Hello everyone, and welcome back to a new episode of EXAPUNKS. In the last episode, we paged a bunch of people and discovered the world is a simulation, and now we're going to build an interface to bridge Ember 2 with our cerebral cortex. Not sure exactly how that's going to fix the problem, but sure. Okay, time for me to eat you. That's your plan, huh? You're dying anyway, so what's the difference? I'll download a map of your brain and run your mind inside of me. Sure. But who cares about my body? I have to ask, apparently, but there's no way to prove that it won't be your death. I mean, it's going to be like death, which you were going to experience anyway. Or maybe it won't be like death. Who knows? You'll have to do it and see. Create a file in your host. Ooh, this is complicated. Create a file in your host containing the host name and hardware register of each neuron exactly once, sorted as pairs from lowest to highest host name. Furthermore, the test runs all have different networks. Do they have the same number of things? I don't know. 4, 8, 10. 4, 8, 11. So, okay, that's been proven. Uh-huh. So... we... Huh. So the first step is even just figuring out how to get an exit into each of these nodes. Right? And also eventually terminate. We don't have to get exactly one exit into each node because we can transmit the host name and use that to deduplicate at the collation layer. But we do have to eventually terminate and stop sending garbage. Oh, and even I was thinking, all right, we'll just sort of send host or nodes into the host, and when you get to a host, you transmit the host name and then a nerve. But the problem is whoever's receiving will have to contend with the fact that multiple messages are going out over the air at once. And it won't be able to correlate the host name we send with the message we send. This seems way harder than everything we've done. Because the others were just sort of data shuffling with you had to be slightly clever with your algorithm. This one, it's not even obvious, any of the steps of this algorithm. Sorting is going to be hard. If they just said, here's a pair, here's a file containing pairs of name value, please sort by value. That's already hard, I think. I don't know, maybe something like bubble sort makes it relatively easy. Slow, but fine, who cares? Or insertion. I guess it would be either of those. They're just both very bad sorting algorithms, and I don't usually think about which is which, but sure. Either one of them, I suppose. Probably insertion sort? I don't know. Shut up. It doesn't matter. Point is, you could sort. It's like not an impossible task. But exploring this network and transmitting its topology back is actually quite difficult. So, what if I was thinking that like the only logical way to do this would be to broadcast global M messages from each node, right? But what if we didn't do that? What if instead exas walked to a nerve and then came back? This sounds difficult, but you could like make a file that the exa carries with them, recording the steps that they took. And then they could trace those steps backward to get to the root again. When they get to the root, they transmit the name of the file they're carrying, and some master collator there picks up that file and concatenates it with the current master file. And at some point you have to determine that everybody's dead. I'm not sure exactly how you do that. Maybe make exas who are about to move broadcast a message on local M saying, yep, I'm still working. And then you just like wait until it's been long enough between those heartbeat messages, because exas should move like quite often. But it'll still take a fair number of moves for the last exa to return home, right? So I guess you transmit messages every time you take a link in either direction, and then that's sort of okay. Whew. I mean, that seems like it could work as a way to explore the network. Copying the file many times is going to be a bit annoying. You'll have to use local M for that. Ugh, which, like... that means... you could be stuck for quite a while, like copying files around long enough maybe for the coordinator to decide you've died. So you kind of need to send messages as you're doing that too. And that's just going to slow everything down so much. All these messages flying back and forth, everyone waiting for the global coordinator. And we don't need to leave no trace. Oh, we do! But I own this. This is my own brain. Or something. It's my brain, right? Yeah. That's actually much harder. Because when you're carrying a file, you, like, if you try to explore to some place that doesn't have a valid link, you just, like, drop the file and you can never recover. You can't allow that to happen. So I guess, though, that's avoidable by you replicate with a direction in mind, and you have the child, the one not carrying the file, attempt to walk in that direction. If he succeeds, he can come back, kill you, and co-opt the file. Although he needs to know the file number anyway, right? To pick it up after he's killed you. So maybe that's sort of silly. Since he needs to know the file number, we can just send the parent. If the parent succeeds, then great. We've moved the file to the place it was to a new. This file shit seems hard. I don't think we're gonna write any code this episode. I think we're gonna think about how to solve the problem and come up with a few approaches that might work. And then I'm gonna have to spend a lot of time off camera on, like, even trying to get those ideas down on paper to see, like, if I can make any progress. And I don't know if I'm gonna, like, get it all in one go and come back and say, here's the answer, or what. But I think trying to solve this one on camera is just too big a task. So we're gonna talk instead about, like, how to do it. Figure out an algorithm that works. You don't need a text editor to program, right? You need your brain. At least when designing an algorithm. So that whole, like, file storing thing, like, it seems okay. It seems extremely slow and rather, like, difficult, but I don't see any fundamental impossibilities with it. You can create a copy of the file and then go somewhere with it. It's, like, hard. It's actually, like, not even that easy after you've, like, say you did all that stuff I just described. You take the file and you walk it in some direction. And you determine that you made it. You can use the contents of the file to not backtrack unnecessarily, that's fine. But yeah, I guess that's true. After I was worried about, like, being able to keep track of, like, which direction you ran. really like to avoid this whole file business. But how else can you do it? If everyone is just screaming stuff out into the void, it doesn't work. They need some kind of coordination. Because you can tell host names from numbers, but if you receive a host name and then a number, you don't know that they're coordinated, like that they're supposed to go together. Is there some way that we could use, like that we could build some kind of lock with the mechanisms that we have now? I don't think so. Like, you could have the coordinator send out a message saying, I hereby authorize one person to send me a message. But, like, there's a lot of reasons that that doesn't work. One is, fine, the first node who's ready to send back will receive that message and begin broadcasting. But in the meantime, all the other nerve nodes will say, hey, someone's sending a message. That means I'm allowed to send my thing, right? And then they'll send it. So I guess you can have it that whether a message is incoming is only one dimension of the data we have available, right? The value of that message is we can also imbue with meaning. We can say, if you are a node who wishes to transmit, and you receive a value which is specifically 9,999, that means you are licensed to transmit. And then you transmit it. Like, you just send your two values and that's it. Meanwhile, the other nodes are listening for their license to transmit. And if they get a value that is not equal to 9999, they say, oh, someone else is sending right now. And I've just stolen their message. I should retransmit it. Right? Combined with, like, exponential backoff, I guess, you would eventually fight your way through all the congestion and the message would get through. But that only solves the congestion problem. It doesn't solve the problem that you can't have the global coordinator sending a message when there might be no nodes left, because he'll just be stuck forever then. So it has to be based on him receiving a message that he can test and see if anyone's sending. Which means it has to be okay to just send random garbage whenever you feel like it, right? Because you can't wait for a message to determine that it's okay. I don't see a way to do this with global M. Yeah, these networks are all like quite different. And you might indeed have to, at any node, travel to any other node. Well, there doesn't even actually have to be a global coordinator, I think, if we use the file model. Instead, you can have each node, when it reaches the top level, pick up the one master file that we're accumulating and add its data to that in sorted order. The problem is, well, there's a lot of problems, but someone else might be using that file. And unlike M, files don't block. You just die if you pick up a file that's not there. So I think it is better to if we're using files, we have to have a global coordinator who receives these files and importantly, you have to actually just receive the file ID, not any of the contents in it. Because those contents, if you broadcast them non-atomically, someone else could be writing their own thing at the same time. I really wish there were some way I could think of to not have to keep a file of like the path back home. I guess I don't. I could just wander randomly. Carry with me a file containing whatever I find. Like, when you are exploring without having yet found a nerve, no. I was thinking when you explore without having found a nerve, you just like kind of replicate at random and move around. Or not at random, but exhaustively. And move around. And if you find a nerve, then you start walking just as randomly. But you make copies of the file every time you step into, like before you step a direction. You copy down the data that you found in the nerve into a file, and then you step around randomly. Bringing the file until, and you check the host name every time you step. And when you get back to the host name, that's the name of like your root host, you say, aha, I'm here. And you drop off the file that you found, right? The data that you had. But that doesn't really work very well because, excuse me, because you have to, after, like, if we did that, then once we got to this node, we'd actually, can I see like what the, okay, so it's not like a do this repeatedly, thank goodness, but just once in each test case. Hang on. What? Who says that we need to replicate into each we need to explore the tree in parallel? Who says that, right? There's a well-known algorithm for finding your way through a maze connected in the way that this is connected, right? If we view this as a maze instead of as a tree and try to follow the left-hand rule, we'll visit every node exactly twice, right? And then, right, we'll go like go through here. Well, not twice. The ones at leaves we'll visit just once, I guess. But anyway, we'd visit each node at least once. And we could, at each step, check, hey, are we back home? If so, drop off the file. Right? These are all, we don't have any loops in them or anything dumb like that. Yeah. Now, like, yeah. That seems much better. Now, what happens, though, if I read the same nerve twice? I'd like to know that quite a lot, please. Do I get the same value again? That would be quite nice. I do. Okay, so I don't need to worry about duplicates. I can just prune those as part of the sorting phase, perhaps. Yes, I had been thinking of this whole process too much like the sort of GPS levels we had, where you just need to get something to every node, and the tree is arranged kind of like, it's not a tree. It's very regular. And in that case, it was perfectly reasonable to say, just go, spawn off a new process for each direction. Here, of course, it's like tricky. Still, following the left-hand rule is a little bit difficult if anytime you try to walk in, if the only way to walk into a direction is to kill yourself, there's going to be some trouble. I guess actually, if you start here and follow the left-hand rule, let's say we pretend we were going in, I don't know, whatever direction. We came in this way, so we were going in the +1 direction. Or the +3 direction, I guess. Wait a minute, this... This is almost a normal nerve structure, right? Or a normal structure for a file. Like, the layout is normally that like -3 is this way, +3 is this way, -1 is this way, and 1 is this way. And therefore, to follow the left-hand rule, you can just sort of cycle through those numbers in like a reasonable way, right? But here, there's this one spot in the graph where the edges are labeled differently. Right? Is that a problem or is it fine? Right? There's like a -3 and a 3 next to each other. Does that matter? Do you actually need to follow the left hand? Or do you just need a consistent, within a node, way to visit? Like, let's say I did the normal left-hand rule thing, and I said that, like, look at this node, for example. If you are going currently in the -1 direction... Oh, wait. No, these are all weird, right? They're not consistent at all. -3 is opposite from a -1 here. And here, 3 is opposite from a -1. Okay. So how many times in a normal traversal would you visit this node that has 4 edges out of it, right? 1, 2, 3, 4, and then out. And it doesn't matter what order you visit these nodes in, so long as the last edge you take is the opposite of the first, is the same as the edge you took to come in the first time, right? Now, it's a good thing they have still maintained the property that the two edges of the doors on the two sides of an edge are negative numbers of each other. Because otherwise it would be quite hard to even like go back the way you came. And that makes a lot of things more difficult. Even like you enter a room and you don't even know like which door takes you back to where you came. How do you explore? You can do it with like hostname lists probably that you've seen before and how many times you've seen them. That seems awful. I feel like this like left-hand rule thing is the best idea I've got, because it makes everything so much simpler than like having a bunch of traversals which each have to know the way back. We just need a consistent exploration and return strategy. I'm just not sure how to maintain this notion of like what exit do I need to follow for this node, right? I mean, I guess that's what a stack is for, right? We need to build a stack that we use to track like the edges we need to follow to get back. Yeah. So maybe the file that we carry with us is in fact, yeah, it's like a list of directions. So when we enter a node, so what we're carrying around with us in like our mental state is whether we are currently pushing or popping things from the stack, I think. So my first like thought is when we first enter a node, we note the direction that we came from and put that on the stack. Then we try a bunch more traversals, which involve pushing and popping things from the stack. But we maintain the invariant that the stack depth, the stack size, is how far we are away from the root. And we always try yeah, I see. We just push -1 onto the stack when we get to this room, and we make sure that -1 is the only thing on the stack. And then we say, well, I'd like to try every direction that isn't currently the top of the stack. But that's even a little bit hard to do. Just because you don't want to spawn off 3 processes for the 3 directions that aren't on top of the stack. Because, or not all at once anyway. Because we need to carry around the file with the stack to help us get back. So you choose one of the 3 directions that isn't on the stack, right? And then you try going that direction, and if it succeeds, you push, you retain the stack and push the thing to the top, and that's fine. My problem is when you, like, okay, we get here, right? We have a -1 on the stack. And then we choose a direction to go in that's not -1. Easy. Let's say we choose 1. And we go in the one direction and it explodes. And we detect that it exploded via, like, whatever. I don't think it super matters. It's possible. We learned to detect X explosions in a previous episode. Then we're here. But okay, and then we say fine. The stack still contains just the number -1. I need to choose a direction that isn't -1. How do we make sure that the direction we choose is not just 1 again, right? That's what bugs me. And I had, just a moment ago, a clever idea that doesn't work. But my thought was, suppose that when we first enter a node, i.e. by pushing a thing onto the stack rather than by popping something to determine that we should go back, we spawn a new EXA who lives in this node. And his job is just to broadcast the 4 directions in the order that, like, or the 3 non-popping directions in the order that we should try them. Then, when you pop your way into a room, you can check, is there a message here? If so, then I'll just go in that direction. The direction that it suggests. Otherwise, I'll pick the file back up and I'll pop. I'll remove an entry and follow the direction it was saying to go. And that actually seems quite good. I think we could successfully explore the entire tree that way. Right? We could visit every node in that way. But how do we actually collect any data? Because we have to also manage to, like, carry a file around, the popping file, and we need to, like, broadcast when we get to a nerve, and that's okay, like we can do that, but I'm just sort of bothered by the way that I was detecting that. The way I had imagined detecting an exa going somewhere was that it would come back, like if it succeeds in traversing, it might like come back and kill the thing that was going to the thing that replicated to it, to say, nope, you're not in charge, this traversal did work, I'm in charge now. We can't do that if there's another exa in the room broadcasting instructions, because you don't know who kill would hit. However, I think you can achieve something similar by using the file that you're carrying, right? You, God, I wish there were a file with just a consistent number here for me, right? What happens if I just make and then file X? It's file 400. Is that, like, reliable? It seems reliable. It's probably even documented. So, okay. What you can do to make sure that there's only one master after this replication and that master knows whether it should continue is, before you replicate, drop the file on the ground. Now, there's no room. There's only 4 spaces in each node. There's room for a nerve and an exa giving instructions and one other exa. Well, assuming you drop the file. So maybe you don't drop the file on purpose. So you're carrying the file when you walk in, right? And you say, oh, let me spawn another exa to give directions. And then you say, all right, I'm going to follow those directions. Let me replicate someone who's going to be here in case I die. And then you leave. If that succeeds, the guy who stayed behind will pick up the file. And he'll say, oh, I guess that didn't work. Let's cross that direction off the list and keep going. But if you did succeed in passing through the node, the edge that you aimed at, then the file won't be there for the other guy to grab, the copy you left behind. He'll grab it and he'll die. So the most space you've used up in a node all at once is a nerve, an exa to give directions, a master exa carrying the file, and a backup exa left behind in case the file is dropped. So that all fits. I think the idea is starting to come together. There's still a lot of implementation work. But my idea is to have a stack on the file of the path we have taken so far. When we get to a node, for the first time, we'll push the link we came through onto the stack. Then, and we'll like have to keep that in X or something. Then we'll spawn a new exa who will, for each number -1, +1, -3, +3, will broadcast that number unless it was the one you had in mind when you entered the room. Broadcasting them each exactly once. Oh, also the first time you enter a room, you should spawn off a new EXA that tries to send the nerve and the host over global M to the coordinator. Wait, do you need to do that? I guess it's fine. You could instead, like, append that to the file, like, and somehow manage both of those things in addition to the directional stack. But it seems cleaner to, the first time you visit a node, when you are pushing its return address onto the stack, you also, before doing any of that, just spawn off an EXA that broadcasts the nerve, and if there was a nerve, the host name, and then halts. So fine, you enter a node, you broadcast these things, or you spawn off an EXA who broadcasts these things. Then you spawn off another EXA who transmits the 3 directions you need to try. And then, for as long as there is a message, no. And then, having done that, you transition into the visit a node state instead of the enter a node state, like the explore state. In the explore state, you check to see, are there directions for me here? If so, attempt to follow them by spawning an EXA in the explore state. Or, well, in the cleanup state that picks up a file, I guess. And then walk in the direction you're supposed to. And jump to the enter state, right? The first time you visit a node. In that new node that you get to. The explore state guy that you or the cleanup state guy that you left behind waits a moment or two and then tries to pick up the file. And if he got it, he jumps to the explore state. Otherwise, he's dead. It doesn't matter what he does. Finally, if you are in the explore state and you check whether there are messages incoming and you see none, you say, well, I guess we're done with this node. You read the file you're carrying, look at the end, and say, this is the direction you should go back. And you go back. And you enter the explore state again to continue exploring the other branches that led from this node that you're revisiting now. If you ever look at the stack to decide where to pop to, and it's empty, then you must be at the root node, the only place where there is nowhere to go back to, and no EXA giving instructions, so you will be in the go back state. At which time, you should wipe the file you're carrying, and what? Broadcast. How exactly do you interrupt this guy when he might be in the middle of sorting something? I guess the best approach I can see is for this guy to switch back to local M and say, hey, is there someone here waiting to kill me? No, because maybe he just toggles back and forth between local and global M, sampling both non-blockingly. If it's global M, he adds the message to the file and gets back to sorting. If it's local M, then he halts the program. That seems workable, although something cleaner should exist. Some way that you can like broadcast a time bomb to this guy, right? Something that like, I don't know, you can't guarantee access to any... Oh yeah, you can. You could broadcast a symbol, right? And there's always a symbol available. It's the host name. So we normally transmit the nerve first, the nerve value, and then the host name. But if we wish to abort the program, we can transmit just the host name and make sure that this guy's code explodes in that case by like iterating over all the values currently in the file. I mean, I don't know, he can just like, it's easy, right? When you receive a value, save it into X and then like divide it by 5 and throw away the result, right? Put it in T or something. Yeah, that works. And then if you didn't explode, then you like take the value and put it at the end of the file. And then like do a bubble sort iteration to actually, is bubble sort the kind of thing you can keep? Like insertion sort kind of makes more sense for what we're trying to do because we don't have the whole array at once. We're sort of inserting values one at a time, and we'd like to maintain the invariant that the list is always sorted. The only real way to do that is to start from the end of the file, scanning backwards until we, and like copying items forward until we find the spot that the new item belongs in, and then we insert it there. But scanning backward is hard because you can't actually tell when you've reached the end of the list, end of the file. So maybe you have to scan forward. Keeping track of how many entries you've scanned over somehow? A little bit tricky, but that's a question of sorting. I'm happy enough with this episode having figured out what feels to me like it might be a working algorithm for exploring this tree. And like, if I'd just thought about this more as a graph traversal problem, I would have thought about it sooner. We just want to do a traversal. And we have like a stack. And like, how do you... I guess thinking of it as a stack was sort of like something that didn't occur to me at first. But we have one, and like, that's a... I don't know, there's a lot of weird mechanics in this game that don't translate cleanly to a normal computer science theoretical notion. And so I'm used to like thinking about these problems from the point of view of this game, which doesn't necessarily translate quite so obviously to the way I like know to think about graphs from like studying computer science. But this is clearly a graph traversal problem. We just need to implement depth first search using a stack, and like then map that back onto the mechanics you have available in the game, which I think I've done successfully. So, I was gonna say now I'm gonna go do that, and the next episode I'll show you guys how it went. But actually now I'm gonna go to bed, and then some undetermined time in the future I'll have some time to work on this, and then I'll show you guys how it went. Okay, well, thanks for sitting with me while we wrote like 2 lines of code the whole episode, something like that. It's an interesting puzzle, and I hope you guys enjoyed this little excursion through thinking about programs. Thanks for watching, and I'll see you next time.